this is the last lecture of our GIAN course, but if you missed the course, and I know some of you did, you don't need to worry about it, because I'm going to show you how to solve these problems without knowing anything about mixed integer optimization. So the theme is mixed integer optimization and differential equations. And I'm going to start with a couple of examples, and just to set the theme. So we're going to start with ordinary differential equations, but I like to start with this example because this is where we're heading at the end of the lecture. So I'm looking at an inverse problem over an advection diffusion equation. So imagine that I have a true source of contaminants, for example, in the subsurface, and this source is subjected to an advection diffusion equation. So there's a diffusion parameter here, which means it moves away from each other. And then there's an advection term, which you can think of a wind or a current that's moving along. And in this case, it's moving from left to right. And so when you solve this differential equation with this right-hand side, the solution that you see is this one here, except for the red dots. The red dots are measurement locations. And you can imagine that you're drilling boreholes and you're trying to measure the contaminants. And from the measurements that you get, you want to invert for the true sources. So this is, in general, an infinite dimensional mixed integer optimization problem where the sources are the right-hand sides of my PDE are binary. Either it's 0 in blue or yellow is 1. And you have this partial differential equation. So I'm going to show you on the next slide how you can make this into a really simple problem. So I've rewritten the inverse problem that you saw on the previous slide over here in sort of much shorter hand notation. So there's the advection diffusion equation. We're trying to invert for this binary indicator where our contaminants are. And typically when we solve partial differential equations, we discretize, and so we replace the functions, the state variables u and the control variables w by some finite dimensional approximation that I indicate with h. So h is the mesh size that I'm going to use. And the way I do it here is going to be the easiest one, which is finite differences, but you can also use a finite element approach, and that's typically a preferred approach when you solve these problems. But I wanted to show you what this looks like in finite differences. So first of all, you have your objective function. So this is really, this operator here is evaluating u at the measurement locations. That's the projection of u onto the measurement locations, and then comparing it to the data that you have at these measurement locations. So that's just a least squares term, and this integral just becomes the summation. The next thing we could do is we can discretize this differential operator. So that's the diffusion operator, and we'll just use a second order finite central difference scheme, which is given here. And so this function that I have here is essentially approximates the second derivative of my function u, which is this term here. So uij refers to evaluating uh at the grid point ih and jh. And then I have the advection term here, and that's just the direction of the advection times the first derivative of u. So that's a finite difference term I have here. I'm using, again, a central difference term. And then the right-hand side. And then the rest are just equations in simple bounds. So this is just, if you look at it, this is just a convex mixed integer quadratic optimization problem. There's a convex objective. The constraints are all linear in these variables uij. And you don't need to know anything about differential equations anymore. You just look at this and say, this is a mixed integer quadratic optimization problem. So if you solve this, unfortunately, and we saw this earlier, the students who were here, the results that you get out of our solvers are not very good. So on the going from top to bottom, I have a number of solvers. There's Skip, there's two versions of BonMin, and there's Minotaur, which is a solver that's developed here at IIT Bombay and at Argonne. And from left to right, you see an increasing mesh size, or decreasing mesh size, increasing number of discretization points, going from 16 by 8 to 256 by 128. And what we're interested in is recovering this red outlined area. That's our original sources. And the solutions that you see are these yellow areas here. So sometimes they're really bad, and sometimes you don't recover anything. And there's lots of spurious solutions that you recover with these solvers. So in this talk, I'm going to tell you how to solve this problem and how to solve it efficiently. So clearly, the solvers, the method that we talked about in the GIAN course, cannot be applied to this problem, and we need to do something different. And this slide is going to be the conclusion. So I'm going to start my talk with the conclusion. So there's a lot of applications that are important in this case, and one that I'm highlighting here is additive manufacturing. So we're trying to create 3D structures by printing materials and layering it on top of each other. And one example is, for example, printing a 3D support for a wing of an aircraft. And the idea is that you can be potentially much lighter than traditional designs if you do this 3D printing. But if you want to solve these problems, you have to model, again, the partial differential equations now in 3 spatial dimensions. And each voxel that you have in your discretization can have a binary variable that tells you whether you place material there or not in your printing pattern. And so this leads to really huge binary optimization problems. If you discretize this, even just on 1,000 by 1,000 by 1,000 mesh, which is probably still quite coarse, you have 1 billion binary variables. And so this is completely impossible for current solvers that we have. The solvers that I showed you on the previous page cannot tackle these problems. The linear algebra is too big for these solvers. The branch and bound search trees that you get will just get massive, and you cannot handle these problems. Now, the good news is, at the end of this talk, I will have given you 2 methods of solving these problems. So there is a simple rounding approach and an improvement heuristic. So I'm going to give you 2 methods which look like heuristics at first, but the cool thing is that they have a global convergence guarantee. So if you refine your mesh, these methods will converge to the global minimum. So this is really cool because rounding is a very cheap way of doing things. You just need to compute a relaxation, a continuous relaxation of your mixed integer optimization problem, and then round it in a clever way. And the improvement heuristic likewise ensures that you get convergence. And this is a weird kind of convergence because it's not convergence for a particular mesh size. It's convergence in functional spaces as the discretization goes to 0 and as you approach the infinite dimensional problem. And there's a bunch of open challenges and problems. So if you like, and you have 5 years left on your PhD, I can give you some problems to work on. Okay, but before we get there, we need to sort of go back a step and go to ordinary differential equation and mixed integer control for ordinary differential equations. So I'm going to start by showing you how to solve these problems efficiently, and then in the next lecture, I'll tell you how to generalize it. So this is a very famous optimal control problem. It's called the Lotka-Volterra model, and it's named after 2 mathematicians, Lotka and Volterra. One of them, I believe, is Italian, and they were looking at the stock of tuna and how many sharks there were in the Mediterranean. And they were observing this oscillatory behavior between the predator and the prey. So the prey would sort of grow, and then the predator would somewhat catch up. So the sharks would sort of catch up because there's more tuna to eat, and then the tuna would die off, and then the sharks would die off because there wasn't enough food anymore. And this dynamics is described by a set of ordinary differential equations, this Lotka-Volterra model. The goal, what we're trying to do is our goal is going to be to try to control this stock of fish so that they converge to a steady state. So we want to get, over time, we have the u is a vector of 2 variables. u1 is the population of the tuna, u2 is the population of the shark, and we want them to converge to 1 in some dimensionless way. So there's not 1 tuna in the Mediterranean, but maybe 1 million or something like that. So that's already been dimensionalized. And the differential equation is given here, and I have the option of, on each day of the year, of basically trying to catch either tuna or kill sharks in the Mediterranean. and there's some coefficient there. So the Lotka-Volterra model without these, the one that gives rise to the oscillation, is this model on the left here, and on the right is my actions that I can take, my control actions. And my control actions are going to be that either I go and fish tuna, or I go and kill shark in every time interval. And a collaborator of mine has solved this problem, and here's sort of a preview. This is what the solution looks like. So you can actually get to a solution where you get to a steady state, and the gray lines here indicate where you're hitting the control, where you're applying the control actions. And there's a couple of things you can look at here. One is that the control actions, there's a lot of forward and backwards between the controls, so there's a lot of bang-bang control that's happening, but eventually you get it to the steady state. And he solved this using a code that was developed at Lawrence Berkeley National Lab. No, it's not, but it's not crucial to have an integer w. The problem is much easier if you don't have an integer w. But we're interested in applications where we need to have the integer w. So where we either, for example, place material or not place material, or where w corresponds to the gears in a car, or it indicates which gear in a car you're driving. And it's much, much easier to solve if w is continuous. And no, it doesn't. Oh, for this problem, it would give you a different answer. The w would be interpreted differently, I think. So there would be maybe a fraction of your fishing fleet would go out. So then that's maybe a way of interpreting it. But we really wanted to we wanted to make it an integer problem because that's the challenge that we're interested in. Okay, so I'm going to develop rounding heuristics, and the main assumption I'm going to make is that if I relax my integer controls, my binary controls, then I can solve the problem efficiently. So the easier problem where I relax integrality is solvable. And that's a reasonable assumption because we can solve PDE constraint optimization problems very efficiently. And there's good software for that. And the goal that I'm going to try to show you here is what I want to find is I want to find a good rounding strategy. So on the right here, I have some continuous control, and if I discretize it, I get the step function, the green step function that I have here, that's between 0 and 1. So this corresponds to not an integer solution, and I want to somehow convert this into an integer solution in a way that allows me to talk about convergence afterwards as well. So I can, of course, do a very simple thing. I can just take my continuous relaxation that I've computed for my binary variables, and if it's greater than a half, I round it to 1, and otherwise I round it to 0. So in each time interval, in each one of these little time slots here, I look at whether it's above the dashed line, that's a half, or below it. And so I would just round all of these to 0, the ones in the first 3 time intervals, and everything else will be rounded to 1. And that might be an acceptable rounding. And so here's an example where I did this on a slightly different control. The green line is this piecewise linear control that I have for the continuous relaxation, and the red is the rounding. So this looks reasonable. This might actually work. It's a bit disconcerting that maybe the area under the red line is much, much larger than the area under the green line. But it can actually get worse. So here are 2 examples, 2 extreme examples where the rounding is arbitrarily bad. Imagine that your controls are just below a half over the whole time horizon. And then you would round that down to 0. So you're not applying the control at all. Or if they're just above a half, you round it all to 1 and you apply the control all the time. So if these were temperatures in your oven, if your oven only had one setting, which is on or off, and you wanted to bake cookies, then if your solution says set it to just under a half, your cookies would not be baked because the oven would stay off. If the relaxation is just above a half, then you would switch the oven on for the whole time, and the cookies would be burned. So and instead, what you need to do is with this very strange oven that either is on or off, you would need to sit there and keep turning it on and off to achieve the temperature that bakes the cookies at the right time. So it's a contrived example, but this is what we're after. Okay, and there's a famous German law. That's the Bierglasenausgleichsgesetz from Bavaria in 1517. And this is applied in pubs in Germany at the end of closing to make sure that when people leave half-empty beer glasses behind, they're rearranged in such a way that they're either full or empty at the very end. So I can illustrate this law to you now, and this is actually the illustration that shows you how we're going to solve these optimal control problems. So I've bought some, they're not glasses, they're just plastic cups, and we're not allowed to have beer on campus, so Ashutosh kindly provided me with apple juice, with non-alcoholic apple juice. There is no beer in this apple juice. And what I'm going to do is I'm going to create a continuous relaxation here. So imagine time goes from for your left to your right. Here, I'm going to create a continuous relaxation like this, just by pouring some apple juice in here. Okay, so this would be a continuous relaxation of our optimal control. The glass being empty would be 0, the glass being full would be 1, and I've marked off the halfway point there. And so one way of rounding this would be simply to throw away this first glass because it's below half. Then I would find more apple juice and fill up this glass to all the way full. This one would be thrown away. This one would be filled up. This would be thrown away, and I would fill this one up. But that's very wasteful, and also it would sort of ruin the carpet out here. So instead, what I'm going to do is I'm going to look at the first glass, and because it's less than half full, I'm going to take this, and I'm going to say, well, I'm going to pour this into the next glass here. And so now I have one integer solution here. So I'm going through time from 0 to capital T, and I look at my next glass. The next glass looks like it should be full, but I don't want to pour any more juice into it. I'm going to take it from the glass that's over to the next side. So I'm going to make this a full glass now. And then now I have an empty and a full glass, and I go to my next glass. So this is again a fractional glass. This looks like it's almost empty, so I'm going to pour this into my next glass. And you can see what's happening now. I have an 0, 1. Now this glass should be rounded up, but I'm not going to just round it up by pouring in more juice. Instead, I'm going to pour in juice from the next glass over. And so this is now full. And then now I'm at my second to last glass. I'm going to pour this into the last glass. Okay, whoa, don't go away. Okay, so now I have almost my binary solution, except for the very last glass. And for this, I need to fill it up a little bit because I'm not quite there. So I'm going to fill this up, and so now I have my binary solution. There's a simple property here that at the very end, I'm either left with a glass that's just under half full, and I drink it or throw it away, or I'm left with a glass that's just over half full, and I need to fill it up. So the only amount of apple juice or beer that I need to fill up or remove is half a glass at the very end, no matter how many glasses you have. If I had 1,000,000 glasses here, at the very end, I would be left with half a glass, over or under. The algorithm that you've just seen is called sum up rounding or combinatorial integer optimization. And so here's a formal definition of this algorithm. We solve the continuous relaxation, so we have a continuous control with the C, which is the green one. That's the continuous, the one that is over continuous variables that's given. And we're going to construct this binary control, the red one, WB, over this time horizon. And what we did was essentially we computed in each glass what was left over with this rounding residual. So we integrate forward up to the time step tk the amount of liquid that was in all the glasses up to that point, and we subtract from it what we had rounded up to the time step tk minus 1, the previous one. So what's left here, this rho k, is whatever is left in the current glass that you're looking at. And then the threshold is, it's greater or equal. If it's greater or equal to a half, I round it to 1. Otherwise, I round that glass to 0. So there's no randomness here in this algorithm. You could introduce some randomness, I think. And so seeing this, I can show this again in action. So this is the algorithm. It's very simple. You walk forward in time. At every time step, you compute the rounding residual, what's left in your glass, and you do the rounding based on that. So in the first time step, I just round down to 0, and my rounding residual is just what was left in the glass. And now I take what I had in this glass, and I pour it into my next glass, That's still below a half, so I round it to 0. Now I take what's left here and pour it into my next glass, and then that's going to be rounded to 1. And now I had to make up the difference here by taking something out of my next but one glass over, so then that's rounded to 0. And if I just keep going like this, that's my rounding that I compute. And again, at the very end, I now have something that's left over. I have half a glass more than I could distribute over the glasses that I had at the end. But there's always at most, there's always at most more than half left or more than half under. And so there's some really nice properties of this algorithm. So this works, and it gives you some convergence properties. Provided your control problem, one, you solve the relaxation to global optimality. So that's quite a strong assumption sometimes, but you can do that in certain cases. There's one really important assumption, and that is my objective function that I'm looking at is independent of the controls. So the controls only enter into the differential equations. We're not allowed to have them in the objective. And we'll get back to that in the second half. That's going to be crucial there. And then there are these simple sort of set of results. So the first one is that you can compare the continuous, the integral over the continuous with the binary solution, and that's almost always at least half a glass. So that's delta t is the width of my glass, the size of my glass, and no matter how long the time horizon is over which I do this rounding, what I'm left over with is at most half a glass. And that means that I can then show, and this is sort of a long 6-page proof that I've summarized here, I can show that the state variables, the state variables are the u's here, they will converge, and then once they converge, because the u's converge, the function values also converge. So this is on a very short slide, the proof of convergence for this method. So in convergence here is in the sense that if I make t, or if I make delta t smaller, so all these quantities have a delta t on the right-hand side. So if I make my delta t, my time step really small, or if you think about the glasses, I had very fat glasses, lots of juice there for you, but I could have made really, really narrow glasses, and then over the same time horizon, this delta t will converge to 0, the states converge to 0, and then I have this convergence. And so I can approximate the solution of my continuous relaxation arbitrarily well with my binary solution. That's what this is saying. So that I can find for every delta approximation error that I want, I can find a delta t time step that gets me within that distance delta. Yeah?
So, we have a very small delta t in number of discrete variables also very
Yeah, yeah. Correct. So that's a great question. So if I make the time step really small, I get many, many more discrete variables. But I never treat them as discrete variables. I solve the continuous relaxation, and then I walk through my rounding. So, and it's magic in a sense, because even though the integer optimization problem becomes much, much harder because you have many, many more discrete variables, this rounding approach now becomes more and more accurate. So you get a much, much better solution out of it. And if you think about it, the reason why it doesn't matter so much is because if the control horizon is very small, then switching my oven on or off for a split second will have very little impact after an hour of cooking my cookies. And so that's the reason. The impact of each binary variable on the solution decreases as I make delta t smaller. And that's, I think, one of the intuitions why this is working so well. But it's counterintuitive. We make the problem much, much harder, combinatorial explosion, but we can solve it much easier or much better. We get better solutions. Yeah?
You're reducing the granularity on the height, you're increasing it on the width.
No, I'm reducing the granularity on my discretization on the step size. So the delta t is from here to there. So the height is always the same. It's always between 0 and 1.
Instead of making the height,
Right, that's correct, yes. And so what I'm saying basically is if I have more granularity on the width, then I can approximate this function much better. And so this is, I show you this on the next slide. So you you can see that as you refine the mesh, you get these bang-bang, what are called bang-bang controls. But the integral that between the difference of the integral between the green and the red curve actually converges to 0. And you can show that the difference, it's lost down here, but the delta difference here goes to 0, and you can see it nicely. Here's another example where I had these controls that were just below a half for the continuous relaxation. I rounded it down to 0, and now I'm doing this continuous switching on and off. So bang, bang control. And if you know anything about control, or if you don't, the one thing you should know is that bang, bang control is bad, because it's like if I take the light switch and I keep switching it on and off continually, I will eventually break something. And so this is not, even though there's a beautiful convergence proof, implementing this in practice is not a good thing. And so this is where we come to some of the challenges that are still out there. And in particular, Sebastian, so here's a sort of summary. This converges in order n steps, or converges in the sense that I can bound the difference in the objective for a given delta t. But the rounding introduces a shattering, this behavior that I go from 0 to 1 at very small or infinitesimal time steps. And that can damage control equipment. So please don't try that with your favorite stereo equipment or Xbox or something like that. There was a thesis, a PhD thesis recently from one of Sebastian Saga's students on how to add combinatorial constraints, things like minimum uptime or minimum downtime. So once I switch the equipment on, it has to be on for a certain minimum amount of time or off for a minimum amount of time. You can also look at minimizing the number of switches that you're allowed to do. And that's a term called total variation. And that adds scheduling constraints to my optimal control problem. I'm not going to talk about this here, but it also loses our convergence property. So we no longer have this nice convergence result. So there's a gap here between what we can prove, which is this for these bang-bang control, this shattering behavior, and where we really want to be, which is where we have additional constraints on the controls. And then it becomes hard again. That's when the problem becomes hard again. So then adding more integer variables makes it much, much harder if I have these minimum uptime or minimum downtime constraints. Okay, so I split this up into 2 lectures. So we're going to go in the next lecture, I'm going to tell you how to extend this to PDE constraints, this idea. We've seen how we can solve optimal control problems with binary or integer controls using this rounding approach. But there are also problems with partial differential equations, and those are much more interesting. I showed you the source inversion problem to find contaminants. I'm going to talk a little bit about topology design optimization, and there's a beautiful book and some papers by Ole Sigmund and one of his co-workers. In the nuclear plant design, in nuclear reactors, you're interested in exchanging fuel rods. So what happens is that after 18 months, you take maybe a quarter of the fuel rods out of the reactor and replace them by fresh ones. But when you're doing that, you also want to reorder all the other fuel rods, so that not all the fresh ones are together, because that would cause potentially a meltdown, or not of them all too far apart. So you're mixing up fuel rods of 4 different generations. And that's, again, a differential equation that models the physics inside the reactor. And then you have these combinatorial constraints on how to arrange the fuel rods. Other examples are the design of next generation solar cells, where you're trying to design a solar cell that allows photons to enter but not exit. You want to design a one-way mirror for these solar cells, and you can do that by printing a sort of 3D space-filling designs onto the coating, and those are gold coatings that you put on there that can have a finite number of angles on which you can rotate them, and then you can reorder or reorganize these cubes in a certain way. We've also looked at the design and control of gas networks. So that's important in the United States, where gas is used for electricity, but also to warm houses and for consumers. And when there's a gas shortage, consumers usually take precedent, and that means that electricity prices go up because you have to use more expensive generation. And so there, one of the things we looked at, whether we can reverse the flow along a gas pipe using a control algorithm. And that's sort of, in principle, at least possible. In practice, nobody wants to implement that. If you want to reverse the flow on a gas pipe, the way to do that is you build a second gas pipe that goes in the opposite direction right next to it. So the problem I'm looking at here, the one that motivates me, is topology design and optimization. And there are two approaches for doing topology optimization or shape optimization for designing shapes. One is shape optimization, which I won't talk about here, where you're given an object with a certain number of holes. This object rests somewhere, there's some symmetry, and you have a certain load. This could be, for example, the outline of a bridge. And then you allow the shape of these holes to change while you're doing the optimization. So you're optimizing with respect to the shape of these holes. Topology optimization is kind of somewhat easier to think about. We start off with a discretization. It could be a finite difference or finite element discretization. And then we have binary variables that we place in each finite element that tell us whether we have material or not. So that's a yes-no decision. And then there are a set of partial differential equation constraints that, for example, tell you how this structure would behave if you had a load that would be applied at this end here, subject to it being fixed at this end here. If you want to play around with these topology optimization problems, there's a very beautiful 99-line MATLAB code by Ole Sigmund. And it has pictures in it. You can change the outline. It does all the finite element discretization for you. So you can just look at what you get at the end of the day. It's really nice. And there's a very good book that describes that too. The challenge that we face is that if I discretize my finite element mesh, so let's say I have triangular elements that I have throughout my domain, and maybe I have some controls, so I decide in each of these blue boxes whether I place material or not. The question is, how do I order these elements? So previously, in the ordinary differential equation case, it was easy because I was just following time. I was just going forward in time to decide how to empty and fill my glasses. But here it's not clear. It's not, if I think of each of these boxes as a glass of beer or apple juice that's fractionally full, I need to find some kind of ordering that gives me, again, convergence in functional space at the end. So that's really hard, or I thought it was hard to do. I tried a lot of different things. I tried following the advection direction. That doesn't quite work because the diffusion gets in the way. But luckily, there are smart people. And so Paul Mans and Christian Kirches came up with this idea of using space-filling curves. So space-filling curves have been around a long time. They're a way of sorting objects that are arranged on a mesh in a single line. So here's how this works. I have 4 elements here, and I just traverse these elements using this black line here. And if I do that, then I lay them out on my line, and I can now apply the rounding approach that I had earlier to this ordering of my elements. And then if I refine this space-filling curve, the way I'm doing it is I'm going to first refine everything that's in my first element here. So my new first 4 elements are these ones guys here that were first in here. And so I can now traverse another curve. And the beautiful thing is that everything that was in this curve or in this element gets refined first and is oriented on my line first, and then everything that was in the second element lies next on my line, and so on. And you can keep doing this, and you get these beautiful curves. And the nice thing is now that when I do this, I have a natural way of refining my curve and orienting my finite elements in an order. So this can be done efficiently, And Paul calls this an order-preserving decomposition. There's other order-preserving decompositions, but if you have these order-preserving decompositions, then you can solve the relaxation of the PDE constraint, or the PDE constraint optimization problem, the continuous relaxation. You get the amount of controls that you have in each element, and then you use one of those orderings and do the rounding on that ordering, and you still get convergence. So this is a very simple sum-up rounding approach that you can take here. I solve my relaxation, I then follow the space-filling ordering to do the sum-up rounding, and I have a solution. And this works remarkably well. So we tried this out on the design of an electromagnetic scatterer. So here's a slightly more complicated equation, but I'll take you through this. First of all, we have an incident wave. This is the magnitude of the incident wave. So this is happening in complex variables, but don't worry about it. You just split this up into reals and imaginaries. U is the response wave. U0 is the incidence wave that I'm showing here. That's going from bottom to top. I have a domain, capital omega, in which I solve my differential equation, and a smaller domain, omega hat, in which I can place my scatterer or my cloaking device. So the scatterer is going to be in each element of this smaller domain. It's either going to be 0 or 1. The boundary conditions here, don't worry about those. And then this is Helmholtz equation. It's no longer a linear partial differential equation. It actually has this bilinear term here, which creates some issues. But this is effectively Helmholtz equation. And the solution U that I get out of here is the wave that's reflected, and I want the superposition of my incident wave and the wave that I create to be as small as possible in this upper domain here, omega 0. So this 2 norm here is an integral of this upper domain here. Okay, and then you can discretize this using a finite element discretization and maybe having a coarser discretization for the controls. And the kind of behavior that you get looks like this. So this is now the solution. We looked at 3 materials. So we have actually 2 sets of binary variables here. It's 0 material if both binary variables are 0. Otherwise, we can either have one or the other material. So we made it slightly more interesting, and this is the objective function in the whole domain. And so what you can see is that your cloaking, blue means low magnitude, you're cloaking quite well up here. You get these beautiful pictures. This is the cloaker that we're designing, and if you can, I'm not sure how well this is showing, but there's a lot of scattering or spackle patterns that are happening here. So there's a lot of zeros right next to ones, and that's really bad. And in particular, this would be hard to implement or build in practice. So we now need a way of somehow reducing these spackle patterns that we get here in order to get designs that we can implement in practice. And there are ways of doing this, before I get to them, I wanted to talk about an improvement heuristic. So one approach is the sum-up rounding approach. I solve the relaxation, I order my elements, and then I go through them in that ordering to round them. An alternative approach is to use a trust region steepest descent method for these problems. And these problems have a really nice property that if I fix my binary variables in these problems, these PDE constraint optimization problems, then my state variables are the unique solution to my partial differential equation. So there's a lot of theory for the right partial differential equations with the right boundary conditions. We can often show that there exists a unique solution. And so that's beautiful because I can now use the implicit function theorem and think of U as being a function of W. And so if I think of U as being a function of W that's defined through my partial differential equation, then I can just replace my objective, which depends on u, by this objective, which depends on u and w. And so this is now an unconstrained problem, other than the binary constraints that I have here. So I've kind of eliminated the partial differential equation constraints. You don't do this explicitly, but you can do this implicitly. So, and this gives rise to a new algorithm that generalizes the trust region approach. So what do I need for this algorithm? I need, so I want to solve this problem here, where now my function u is defined implicitly as by solving this partial differential equation. And so what I can do is, when I'm given a particular control, I can solve my partial differential equation for the state variables. So to get u of wk, in order to find u of wk, I need to solve my partial differential equation given the wk. And then once I have that, I can evaluate my objective function. And there is a related partial differential equation called the adjoint, you can sometimes think of this as the transpose. If it were a linear differential equation, then you solve with the transpose of that in some cases. And solving with this transpose, I can also obtain the gradient. So there's an efficient way of obtaining both function values and then gradient information for these problems. And that's a traditional approach in partial differential equation constraint optimization. And so given that, I can set up a local linearized problem where I minimize a first order Taylor approximation to my objective function. So this is just evaluating the objective at a point wk, getting the gradient, and then evaluating the gradient, against the displacement in w. So this is a first order approximation of my original function. And what I'm going to do is I'm going to add a trust region to this. So I'm going to restrict the step that I'm going to take. And the right trust region here turns out to be the L1 norm trust region, which is also the Hamming distance for binary variables. So this one norm trust region here is a constraint on how many binary variables I'm changing from 0 to 1 or from 1 back to 0. So this is a problem that I can now solve efficiently, even in a large-scale case, because if you look at this, if you stare at this long enough, this is a knapsack problem. And the reason it's a knapsack problem is because you can rewrite this one norm constraint as just a single linear equation in the binary variables, or inequality in the binary variables. Okay, and with that, I can set up an algorithm where I start at an initial, maybe a solution that I have given through sum up rounding, and I'm now trying to improve it by solving a sequence of linearized problems within a trust region. And so once I do that, I need to evaluate the new point. I get a new point w hat, evaluate that in my objective function, and then if I make progress, I take the step. If I reduce my objective, I take the step. Otherwise, I reject this step and reduce my trust region. And the way we've implemented this is actually the initial trust region radius is a power of 2, and we're just half or double the trust region on every step, and that means we stay within powers of 2, and then we stop the algorithm once the trust region drops below 1, because once delta k is below 1, then in this problem I can no longer move from the current point. Okay, so this works really well, and so for example, for this discrete source inversion advection diffusion problem that I had at the very start, we can now solve this not just the 2D problem, but also in 3D. So in 3D, we have 3 contaminants that are maybe underground. We have these wells that we're drilling to try to identify where they are. And one of my students created some Julia code and Ampel code that you can actually get and look at the solutions of this problem. Previously, we didn't get good solutions, so now we get really good solutions. So we can identify this. These are different algorithmic options for the algorithm, different ways of rounding the initial solution, and then different ways of solving and setting up the trust region subproblem. But most of them get good solutions. This first option isn't working very well. but we have other ways of solving this problem. And in particular, this is for the largest. This is 256 by 128, so we get really nice solutions in that case. And this is just a convergence plot for the three-dimensional instance. So here, what you see on the left is the reduction in the objective function value that we see from the initial rounding. So that's maybe not too impressive. That's a few percent reduction. And here you see the evolution of the trust region radius that's sort of on the left-hand side here. So we go up to 128, eventually reduce it down to 1, and then stop. You can do convergence analysis on this. And so Mirko Hahn, who is a PhD student of Sebastian's, he studied this topology optimization problems. The convergence analysis is really quite involved and involves a lot of functional analysis. But for these problems, you can show similar results that if you refine the mesh, you get arbitrarily close to a stationary point. So there's a stationarity condition that you can show, and I'm not going to go into the details. He has a way of doing a Taylor expansion over sets. And so that's the right notion of how to prove convergence here, because you're no longer working with individual integer variables. You think of those as indicators of a set, and then you work in the Taylor expansion of those sets. So that's a concept lifted from topology and shape optimization. And then you can show convergence if you work with very difficult sort of concepts there. So I shouldn't really show that. The last thing I wanted to talk about really briefly is how do we get rid of this scattering? So I left you hanging a little bit that we have this scattering behavior that we see when we apply the sum-up rounding approach. And one way to do this is actually to clean it up afterwards, but solving a different problem. So you need to set up a different kind of problem in order to get rid of the scattering. And one way to get rid of this is to use a regularizer, a total variation or TV regularizer. So this is a term that you would add to your objective function, the original objective function, for some alpha that sort of balances the original objective of cloaking as well as possible versus not having too much scattering. And so you can set up this problem, but if you set up this problem, you can no longer use the sum-up rounding approach, because the sum-up rounding approach is dependent on the fact that the objective doesn't depend on the controls. So now the objective function here that I have set up now depends on my controls, and so this rounding approach no longer works. But we can still apply the trust region approach, and that's what we did. So Paul Muntz coded this up. These trust region subproblems are really, really hard. So we're doing this on I think on a 256 by 256 mesh. So there are something like, I think I had it on the earlier slide, there's of the order of sort of close to 100,000 binary variables. And so we solve these trust region subproblems using Gurobi, because we don't have any other way of solving these problems. We don't know how to solve them. They take a long time to solve. So Paul Muntz set this up, and it took a 2-week marathon solve on a dedicated machine with a lot of memory to get this cleaned up solution here. So there's a lot of work to be done yet, namely solving these trust region subproblems is not easy. And so finding ways of solving them is really important. What we're doing at the moment at Argonne is we're looking at randomized methods using sort of some theory from integer optimization to generate good steps and randomly taking steps to approximately solve this trust region subproblem. One of the things you have to realize is that we're not really interested in the solution to this problem. We just want to make progress. We just want to reduce the objective a little bit. And as long as we can keep doing and making progress, we're doing okay. And so we're trying to find a good way of solving these problems. But this is really, really hard if you wanted to do this with a state-of-the-art solver. And Gurobi is not written by me. The 2-week marathon was done by me. Gurobi is a solver, so this is sort of misleading citation there. I apologize for that. I hadn't realized that earlier. Okay, so almost at the end. So these are really challenging problems, but we're getting to grips with solving these mixed integer PDE constraint optimization problems. And we have these two classes of methods, this rounding approach, which is you take a bunch of beer glasses and you reorder the beer glasses, resort the beer glasses, and you can do that by using the space-filling curve in your 2 or 3 dimensional PDE, and that's an efficient way. But it gives you the scattering, it gives you this on and off that you keep doing, and so those are not things that you can implement. So instead then there are these trust region methods which also have some convergence analysis in functional spaces. And that would be a whole talk to tell you how to do this. And we've looked at connections between these two methods. There's a lot more to be done. So another problem I'm working on is optimal experimental flight paths for ice sheet measurements. So this is also a PDE constraint optimization problem, but it's a much more complex PDE. So this is a Stokes flow. What you see here is the outline of Greenland, and the red and blue corresponds to the amount of uncertainty that we have about the thickness of the ice shelf over Greenland. We're interested in the thickness of the ice shelf. We want to estimate this as close as possible because we can then use the Stokes flow equation and measurements of the velocity over time to deduce what's underneath the ice shelf, what's the basal friction parameter that keeps the ice on Greenland. And that's a really, really important quantity to know because it tells us how long it's going to take until all this slides off. And the uncertainties here are quite large. So the thickness of the ice shelf over Greenland is about 3 kilometers. The uncertainty, the largest uncertainty is around 600 meters. So that's a 20% uncertainty. And that's, if you then think about it, you're now trying to solve an inverse problem for this basal friction parameter where the inputs are uncertain, the outputs are also going to be uncertain by 20%. And then God knows what happens to the predictions that we get out of this. But very important, what we're trying to do then is design flight paths that are not just straight lines. So on this picture you see where NASA and other agencies have flown aircraft across, and wherever there's a straight line, they've flown an aircraft that can measure a path of about 70 meters wide. They have ground penetrating radar that tells them very accurately what the thickness is. But we want to fly different flight paths. We want to fly curves and other interesting things to maybe reduce the uncertainty where it's most significant. And so this is a really, really challenging problem, but it's also a very cool problem. And there's connections to integer optimization again, because you can think of a flight path that's, you can lay down a network and you can look for a shortest path through your network. But the coefficients or the weights coefficients, those are hard to work out in that case. So this is some of the problems I'm working on right now. I have lots more slides, but I don't want to keep you any longer. Thank you so much. You've been very patient, and I'm happy to answer questions if I can. Yeah?
Sampling the applied in any of the steps, for example, smoothing steps that you had explained by using total variation.
Yeah.
So is there a way of applying sampling to say,
yeah, but that's a really good idea. So some form of sampling. We're looking at, there's something called a Graver basis, which connects any integer point to the solution potentially of the integer optimization problem. So it's a very big construct that's exponential. But we're looking at finding sampling this in some way, sampling good steps. So that's certainly the way to do this. This is not, we need randomization here, that's certainly true. So deterministic methods are unlikely to solve this problem, at least for the foreseeable future. I should say these are my friends that have worked with me on these problems. So there's a lot of people here standing behind these slides and this talk. So, and somebody actually, Minali Sharma, she was a PhD student here at IIT, so she worked with me on this too. Cool. Okay.